Good evening, and I welcome you all for the week 7 live interactive session for the course Polymers, Concepts, Properties, Uses, and Sustainability. So now let's get on to the session. I'll just share my screen. Hope you are able to see my screen. Are you able to see my screen, Dr. Ken? Dr. Ken, are you there? Yeah, okay, fine. Okay, let's get on to the session. My my recording also started. So week 7 had 7 lectures, and the lectures majorly covered on viscoelasticity in polymers. So lecture 45 was on brief introduction to the viscoelasticity, and it was on concepts. So what is a viscous response and elastic response in molecular perspective was discussed, where in elastic response as well as in pure elastic and pure viscous response, the history is not considered. And also in case of elastic response, it is more of a storage response. And the current state of stress and current state of strain are considered, whereas the viscous response is a dissipative response. And the current state of stress and the current state of strain rate is considered here. So what about the viscoelastic response, and what are the contributions? What is the Deborah number, which considers the experimental time scale and the materials time scale, and what are the terminal responses? Okay, and what is the elastic, viscous, and viscoelastic response as a matter of time? They're all discussed in the uh, lecture 45. And what happens when a polymer sample is subjected to creep and recovery, right? And how does the response look for a elastic solid and for a viscous liquid, and also for a uh, viscoelastic material, especially how does it looks when it is when a creep response is seen for a microsecond, stress is applied for a microsecond. And for what happens when a response, how does the response look like when it is going to happen for a years together. So these were all discussed in the uh, viscoelasticity introduction. Okay. The next lecture was on thermal response. Again, here it was on concepts. So, what is high temperature response for different polymers were discussed, and then what are the thermal signatures, right? Were discussed, correct? And then, uh, you know, uh, what is an annealing, and the instrumentations like DSC, TGA, TMA, which are used for analyzing the thermal response of polymers. And DSC, the response of DSC was discussed in details, and then thermal conductivity of polymers was discussed in detail. Uh, Hope you are able to follow, right? Are you able to follow? Are you able to recollect if you have gone through the lectures? Okay, fine. Okay, let's proceed. So next, in lecture 47, for the viscoelastic characterization was introduced. And what are the quantitative measurement of polymer viscoelasticity? So what is a static test and then dynamic test? So and how how do you design the dynamic test based on theories and experiments, right? What are the parameters, right? What are the control variables, measured variables, and how how do you define the response, and what type of deformation happens in ideal case were all discussed. Right. And then what are the type of deformations, so the type of deformation, and what are the kind of tests that can be done. Tensile, it can be either a tensile test or compressive test or a shear test and flexural test, and what are the geometries to be considered. Right. The geometry can be a sheet like geometry or a disc like geometry, dog bone shape. So these, deciding the geometry is based on how the stress transfer is going to happen, how are you going to grip the material and all. Right. And what are the controlled and measured variables. Say for example, for a creep test, it's a constant stress that is applied and the output is a strain with respect to time, whereas in case of a stress relaxation, it is a constant strain that is being applied and the output is the stress. In case of oscillatory shear, it is a sinusoidal stress or strain and the output can be sinusoidal, again strain or stress. And these are certain kind of tests that are being conducted, but the combination, permutation and combination are even more, depending on what is the application you're looking for, or what kind of information you want to really get. So based on these, the type of test, the dynamic testing is decided. Right. And uh, what is the response variable in case of creep. So in creep, the response variable is your compliance, right? Because the compliance is nothing but strain as a function of time over the constant stress, whereas in case of stress relaxation, it is the relaxation modulus, just as stress as a function of time over constant strain. And how does these parameters, the response variable, appears for a viscous material and for an elastic material were also discussed. So for a viscous material, for a creep compliance, the creep compliance is a linear function of time, right? It is directly proportional to time, whereas for elastic solid, it's a constant value and an instantaneous value. Right. Right. And if it is going to be a modulus, then for a viscous material, it is going to be 0, whereas it is going to be a constant value again for an elastic material. Right. And viscoelastic material, it is going to be a function of time. Right. And then the next lecture was on simple models on viscoelasticity. So when is viscoelasticity very important? So that was discussed. Right. What are the relaxation times, relaxation modes? So what happens when there is a very fast relaxation mode, and what happens when there is a very slow relaxation mode. Very fast relaxation mode means you will have viscous contribution that is dominating, whereas when the relaxation modes are very slow, then it is going to be the elastic contribution that is going to be dominating. And then there was discussion on the Voigt model and creep response on Voigt model, and on Maxwell model, and on the stress relaxation response of the Maxwell model. So these were all, and these are all based on the discussions were based on the linear response of these models. Okay. And then lecture 49 was on properties. Right. You're there. Okay. So lecture 49 was on properties. So the oscillatory testing was discussed, where a sinusoidal wave is wave of either stress or strain is applied. Right. And in case of a viscoelastic material, there will be a phase lag in the response. Right. So these were all discussed. And then what are the different geometries and fixtures in case of a dynamic mechanical analysis, and what are the rate and frequencies. So it has certain frequency limitations also. For example, you will have some, you can analyze some 0.001 hertz to approximately 100 hertz in a dynamic mechanical analyzer. Right. So these were all discussed. Right. And then what is the temperature control? What are the regions of viscoelasticity was discussed again. And what is the temperature range in which the dynamic mechanical analyzer can be used. And what are the different regions of viscoelasticity? In different regions of viscoelasticity, again, the glass transition, and the glassy region behavior, and the rubbery region behavior, and how does material behavior varies in rubbery region for a cross-linked polymer, and for a crystalline polymer, for an amorphous polymer, right? These were all discussed, right? How does the E prime and E double prime and tan delta varies, right? These were all discussed in dynamic mechanical analysis. And lecture 50 was on damping application, where the concept of energy dissipation during a stress strain cycle and energy storage during stress strain cycle were discussed. And then the damping of vibration and sound absorption, the concepts were discussed, right? And the damping efficiency, right, which is the energy which is the ratio of the work, or the energy during dissipation to the energy during storage. It's the ratio of energy during dissipation to the energy during storage was discussed. And then what is the viscoelastic response of a rubber was discussed. And standard linear solid model, which is the model used for rubbers were discussed. And what are the damping materials available? So these were all discussed in the lecture 50, right? And lecture 51 was on time temperature superposition. So the linear viscoelasticity. So only in the linear region you can have this time temperature superposition, right? The Boltzmann superposition principle was discussed, and the viscoelasticity in polymers and their temperature effects, and time temperature equivalence, and how do you shift the data, right, when you have because you cannot practically do for a very long time, so you do it at a much more stringent conditions, and then you shift the data and prepare master curves. So these concepts were discussed in lecture 51. And then the last lecture for the week, lecture 52, was on impact and energy absorption. So what is a high rate of loading? So, and then energy and stress intensity, what are the failure process, energy under a stress strain curve, fracture energy, stress strain intensity factors were discussed. And then the polycarbonate ABS blends and alloys, right? And the impact strength, what are the commercial tests available, like ISO test, Chappie test, and values for different polymers were all discussed in lecture 52. Okay, hope you're clear. Now can we proceed with the practice assignment questions? uh, okay, okay, that's nice. Now let's proceed to the practice assignment questions. So the first question is, from the dynamic mechanical analysis of a polymer sample with a phase angle of 30°, the relationship between storage and loss modulus can be expressed as dash. Can it be expressed as E prime is equal to square root of 3 into E double prime, or is it 2 E prime is equal to square root of 3 into E double prime, or is it E double prime is equal to square root of 3 into E prime, or is it 2 E double prime is equal to square root of 3 into E prime? So, how do you find out the relationship between the storage and loss modulus? We have the information on the phase angle for a polymer sample from the dynamic mechanical analysis. So, how do you do? How do you go about this problem? This is a GATE 2022 question. So, any idea? So, we have the phase angle data from the dynamic mechanical analysis. Now, we have to find out the relationship between the storage and loss modulus from this phase angle. So, how do you do that? Any idea? Okay, please. So, I'll just proceed with the solution. So, given the phase angle is 30°. So, you have the relation tan delta is equal to loss modulus divided by the storage modulus. So, from this, you have the tan delta, the delta value, that is 30°. So you can find out what is the tan delta value, and then you can find out what is the relationship between E double prime and E prime. So now can you just calculate what is the relation between the E double prime and E prime? Can you just calculate? Are you making a try? It's just the mathematics. Now you have to find out what is tan 30 degree. And then find the relation from the options. You have the options, four options displayed on the screen. Yes, you're right. So tan 30 is nothing but 1 by root 3. So you get the relation E prime is equal to square root of 3 into E double prime. So option A is the right answer. Okay. So let's proceed to the question number 2. A 3 mm thick layer of softened PMMA at 190 degree is sandwiched between two flat parallel plates. A shear stress of 100 kilopascals is applied to the softened polymer. Assuming the softened polymer as a Newtonian fluid with an apparent viscosity of 3 into 3.9 into 10 power 4 pascals against, the relative sliding velocity between the two plates is dash millimeter per second. So you have the polymer PMMA. It is at 190 degree and it is softened. It is in its softened state, and the layer thickness of PMMA is 3 mm. It is sandwiched between two plates. Okay, and the shear stress of 100 kilopascal is applied to this, and the apparent viscosity of this PMMA, softened PMMA is given, and they have also asked us to assume it as a Newtonian fluid, and they've asked what is the sliding velocity between the two plates. So how do you proceed it? Any idea? So you have the information that it is the polymer is sandwiched between two plates, and it is assumed as a Newtonian fluid, and its apparent viscosity is given and the shear stress applied is given. Now you have to find out what is the sliding velocity. So how do you go about this? So there is nothing right and wrong. You can just make an attempt. In fact, you can answer this question if you have an idea on the basic fluid mechanics. Are you giving it a try? Okay, no worries. Now let's proceed to the solution. So as I said, the material is over 190 degree at 190 degree and it is softened. They have given it as a assume it as a Newtonian fluid. They have given the shear stress and they have given the viscosity also. Now, so thickness of PMMA is also given, which is 3 mm. So why is 3 mm? So applied shear stress is 100 kilopascals and apparent viscosity is 3.9 into 10 power 4 Pascal seconds. Okay. Now assumption is it is a Newtonian fluid. So what we can apply is your Newton's law of viscosity. So Newton's law of viscosity is shear stress is equal to your apparent viscosity into your velocity gradient, right? So you have your shear stress which is given as 100 kilopascal and your apparent viscosity 3.9 into 10 power 4 Pascal seconds. You are also given that the thickness of PMMA layer is 3 mm. So substituting all these, you can find what is the sliding velocity between the plates. So just substituting it, right? So it is nothing but your sliding velocity is equal to 100 into 10 power 3 into 3 into 10 power minus 3 divided by 3.9 into 10 power 4. So you end up with your apparent viscosity, your sliding velocity between the plate is 7.692 millimeter per second. So this is how the PMMA is between the two plates. So you can just see, uh, the two blue lines which are the parallel plates, and in between this, the PMMA is placed. Okay. Next question. Hope you understood. Were you able to follow the solution? Yeah. Okay. Next question. The relaxation time for a rubber band at 23 degrees is 60 days. If it is stressed to 2 megapascal initially, then the time required before the stress relaxation to 1 megapascal is dash days. So it is again a GATE 2017 question. So here you have a rubber band. It is at 23 degrees. Okay, and the relaxation time is given as 60 days. They've also given that it is stressed initially, the initial stress is 2 megapascal and there is a stress relaxation process that's happening. So, and the relaxed stress after a particular point of time is 1 megapascal. We have to find at what point of time or at after how many days the stress relaxes to 1 megapascal. So if the stress has to relax to 1 mega, so this process happens basically when you're maintaining the strain, there will be a stress relaxation. Okay, you're maintaining the strain in the rubber band. So the stress relaxation happens. So you're giving a constant strain. The strain is maintained and the stress, decreases. Okay, since there is a relaxation that is happening within the polymer. Now we have to find out what is the time at which the stress has relaxed to a value of 1 megapascal. Okay. Okay, that's nice. You were able to solve it. That's great. 41.8 days. Good. So for the benefit of others, let's share the solution model. Given relaxation time for a rubber band at 23 is lambda is equal to 60 days and initial stress sigma naught is equal to 2 megapascal. So sigma is given as 1 megapascal. The time required for stress relaxation to 1 megapascal is what is asked. So assuming Maxwell model, you have sigma of t is equal to sigma naught into exponential of, there is a exponential decay. So exponential of minus t by lambda. So you have sigma at particular time t, the value is 1, sigma naught is 2 and lambda is 60. So substituting the values, you will get t is approximately 41.6 days. Okay. This is again a GATE question, GATE 2017 question. Okay, now let's proceed to question number 4. Damping factor of a solid polymer under sinusoidal loading in single cantilever mode showing 80% recovery in modulus is dash. This is a GATE 2015 question. So they have given a solid polymer, sinusoidal loading is done in single cantilever mode and there's a 80% recovery in modulus. They have asked what is the damping factor for this solid polymer. So how do you go about it? How do you go about this question? How do you find out the damping factor for this solid polymer? Are you giving a try? Good. So how did you calculate it? Twenty by 80. Okay. So how did you arrive at this 20 by 80? Tan delta. Perfect. Very good. Yes. So your damping factor is equal to tan delta, which is equal to loss modulus by storage modulus. So they've given 80% recovery in the modulus. So if there is a recovery means it is a storage modulus. So storage modulus is 80% and loss modulus is the remaining 20%. So the damping factor is tan delta, which is nothing but equal to 0.2 by 0.8, that is equal to 0.25. Okay. Next. The next question is, the impact strength of polystyrene can be enhanced by blending or mixing with what material? Is it carbon black or PMMA or polybutadiene or glass fiber? So when you mix which of these materials with polystyrene, there will be higher impact strength. Any idea? C. Perfect. Yes. Why C? Okay, you're saying C or A. So which one is the final answer? Yeah, okay. Okay, since I told C, okay, it's a rubber. Yes, perfect. So the answer is when you mix, polystyrene with, polybutadiene, which is nothing but a synthetic rubber, the impact strength is increased, is enhanced. Okay. This is again GATE 2018 question. Next question. The stress relaxation equation for a polymer is given by sigma is equal to sigma naught into exponential of minus T by tau, where sigma is the stress at any time instant t, sigma naught is the initial stress and t is the relaxation time. The relaxation process is temperature dependent and follows Arrhenius law. For a rubber sample, the relaxation time is 60 days at 25 degrees. If activation energy for relaxation is 30 kilojoule per mole, the relaxation time at 35 degrees will it be 30.5 days or 35.5 days or 40.5 days or 45.5 days? So how do you calculate this? So they have given, stress relaxation equation for a polymer, and they've also given the relaxation process is dependent and follows Arrhenius law. For a rubber sample, they've also given relaxation time of 60 days at 25 degrees. They've given activation energy of for relaxation is 30 kilojoule per mole, and they've asked what's the relaxation time at 35 degrees. So how do you go about it? Okay, I'll proceed with the solution. So relaxation process is temperature dependent and it follows Arrhenius law. So why does it follow any Arrhenius law in this case? They've given it follows Arrhenius law. And also if you just consider the temperatures, one is 25 degrees for which they've given the information, the other temperature is 35 degrees. So uh, so if the material is following Arrhenius law, that means it is probably far away from the glass transition. Otherwise, if it is closer to glass transition, then you use the WLF relationship. Okay. Now the Arrhenius law is lambda, that is the relaxation time is equal to exponential of your activation energy by RT. So you have lambda 1 is 60 days at temperature T1, that is 25 degrees. That is nothing but 298 Kelvin. So lambda 2, that is a relaxation time for 35 degrees. We do not know. That is the question asked. So they've given the temperature the T2, which is 35 degrees. That is nothing but 308 Kelvin. We have our value as 8.314 joule per mole Kelvin. And they have also given the activation energy 30 kilojoule per mole, which is nothing but 30 into 10 power 3 joule per mole. So you can just substitute this. So lambda 2 by lambda 1 is nothing but exponential of EA by R into 1 by T2 minus 1 by T1. Okay. So we are just writing these equation, for each case together, combining each case together. I mean, dividing the, Arrhenius relation for, the relaxation time at temperature T2 divided by Arrhenius relation for relaxation time at temperature T1. So you will end up with this relation. Okay. So once you substitute all the values, you have lambda 2 by 60 because is equal to exponential of 30,000 by 8.314 into 1 by 308 minus 1 by 298. So you will end up with lambda 2 is 40.5 days. Right? So since the temperature is increased, so it relaxes, the relaxation time is much faster. Right? It relaxes in much shorter time. Right? In 40.5 days. Unlike at 25 degrees, it takes 60 days. Okay, you can find out how there is a time and temperature correlation, right? Time temperature equivalence, right? Okay, now let's proceed to the next question. Match the following changes observed in calorimetric analysis of a polymer sample when heat flow is in the y-axis is plotted against the temperature in the x-axis. So they have given three conditions. One is step increase in heat flow, next is the exothermic peak, and then endothermic peak. So they've also given what are the changes observed: crystallization, melting, and glass transition. Now we have to match which of these steps indicate which of the microstructural change. Okay, so let's start with the first one. Step increase in heat flow. Which transition or which change indicates this is indicated by the step increase in heat flow? Glass transition, yes, perfect. What about exothermic peak? What about exothermic peak? Is it indicating crystallization or is it indicating melting? Okay, you're saying exothermic peak indicates melting. So, and the third option you're saying that means endothermic peak indicates crystallization. Now let's see what are the answers. Because actually, as you said, step increase in heat flow represents the glass transition. Exothermic peak, it indicates crystallization. Okay, when material crystallizes, there is a liberation of heat, and when melting, the bonds has to loosen out, right, for melting. So it needs some energy for for you to melt. Not only in case of polymers, but in any kind of materials, you have to supply energy for melting. So it is an endothermic peak. This is one of the classic uh, example showing the output of a DSC. So you can see the exothermic peak. So there's a step change. Of course, here they have given step increase in heat flow. Here actually there is a step decrease in heat flow. And then you have the crystallization, which is nothing but your exothermic peak, and your melting, which is nothing but your endothermic peak. Okay, this is the positive side of your heat flow. This is the negative side of your heat flow. Okay, now hope you got it. Now let's proceed to the next. Notched impact test of plastic decreases with increase in notch tip radius, increase in notch depth, increase in temperature, or decrease in notch depth. So, which one of these happens? So the notched impact strength of plastic decreases. Does it decrease with the increase in notch tip radius, or does it increase with sorry, does decrease with increase in notch depth, or does it decrease with increase in temperature, or does it decrease with decrease in notch depth? Okay, you're saying the impact strength decreases with increase in notch depth. Yes, you are right. It increases with, sorry, it decreases with increase in notch depth. Okay. Let's move on to the next question. For a viscoelastic material behaving as a Maxwell model, the modulus at its relaxation time under constant strain reduces to dash. Does it reduce to 36.8% of its initial value, or does it reduce to 63.2 of its initial value, or does it reduce to 66.7 of its initial value, or does it reduce to 33.3 of its initial value? To how much does it reduce? They have given the material follows Maxwell model, and then they are asking for modulus at relaxation time. So how much does it reduce? Okay, now let's go. So Maxwell model means sigma of t is nothing is equal to sigma naught into exponential of minus t by delta. Here they have given t is equal, sorry, t by lambda. So here they have given the time is equal to its relaxation time. That means they are asking the modulus when the time is equal to its relaxation time. So you just have to substitute so t is equal to lambda. That means so t by t or lambda by lambda, that is nothing but 1. So you have sigma of t by sigma naught into exponential of minus 1. So you get sigma of t is equal to 0.368 of sigma naught. So it is, so your sigma t is nothing but reduces to 36.8% of its initial stress. So, for stress relaxation, again, your strain is constant. So, obviously, sigma of t by epsilon is nothing but E of t, right? And your sigma naught by epsilon naught is nothing but your uh, my initial modulus. So there will be a 36.8 decrease in the modulus also. Okay. So option A is the right answer. Hope you got it. Now let's proceed to the next question. Strain gamma in a polymer melt varies with time on application of stress S by the following relation. Eta into d gamma by dt plus g into gamma is equal to S. So, where your S is your stress, gamma is your strain. So, d gamma by dt is your strain rate, eta is your viscosity, okay, and g is your elastic component. Eta is your viscous component and g is your elastic component, okay. So, if a steady shear stress S0 is applied, the strain at steady state is gamma naught, and it is given by, is it given by S0 by G, or is it given by S0 by eta, or is it given by S0 into G, or is it given by S0 into eta? Which of these? You're saying it is S0 by G. How did you arrive at this? I'm not saying it is right or wrong, but how did you arrive at this answer? Rate of strain is 0. Perfect. Why do you say rate of strain is 0? What made you assume that rate of strain is 0? At what time is stress and strain equal? Okay. Okay, let's proceed. Actually, I know there is your assumption is right. Rate of strain is equal to 0. But what is the hint for that is that they have given strain at steady state. So steady state means the rate of strain or is or change of strain with respect to time is 0, right? That is what the steady state that is what steady state means. There is no time variation. Okay, so that is the assumption. Okay, so they have given steady shear stress is S0. They've asked strain at steady state. So at steady state, d gamma by dt is equal to 0. That is nothing but strain rate is 0. So gamma is equal to, as you said, S naught by G. So, when you substitute that d gamma by dt is equal to 0, then you end up with uh, G into gamma naught is equal to S naught. Okay. So, gamma naught is equal to S naught by G. So, as you said, it is option A is the right answer. Okay. Now, let's proceed to next. Deborah number is a ratio of dash. And the next part of the question is, when Deborah number is very small, then the relaxation process would lead to dash. So the first part is asking what is Deborah number. What is the definition of Deborah number, and when the Deborah number is very, very small, less than 1, since it is a ratio, the maximum since it is a ratio, so you have when the Deborah number is very, very small, that is very, very much less than 1, then the relaxation process would lead to what type of behavior, whether does it lead to a elastic kind of behavior or viscous like behavior. This is what is the question. So any idea on Deborah number? You want to take a guess, or do you remember what is Deborah number? Okay. So Deborah number, it is the ratio of relaxation time to the experimental time. Okay. Or it is the ratio of material time scale to the experimental time scale. Okay. When your Deborah number is very much less than 1, that means your relaxation time is very small, or your experimental time scale is very large. Okay. When your relaxation time is very small, when lambda tends to 0 or experimental time scale tends to infinity, then it is the viscous behavior, because your relaxation time is very small. That means the material is able to relax almost instantaneously. That means your dissipation of energy is almost instantaneous. That means it is a very viscous kind of behavior. Okay. Okay. Now let's proceed to the next question. Dash refers to use of thermal energy for rearrangement of molecules, uh, or crystalline phase or blend domains and copolymer domains in polymers. So, what is the term, or what is the process that is done for rearrangement, where thermal energy is used for rearrangement of molecules or crystalline phase or blend domains or copolymer domains in a polymer? Use of thermal energy for rearrangement in polymers. What is this process called? Yes, perfect. Annealing. You have already replied. Good. Next. Formed polymers have dash thermal conductivity than normal polymers. Does it have higher thermal conductivity or lower thermal conductivity or similar thermal conductivity or none of the above? Lower. Yes, perfect. They have lower thermal conductivity. So here are a set of values. So polymers in general, they have a thermal conductivity in the range of 0.1 to 0.6 watt per meter Kelvin. Whereas formed polymers, okay, uh, so they have a thermal conductivity of the range of 0.01 to 0.08 watt per meter Kelvin. So they really have one order lower values of thermal conductivity compared to a normal polymer. Okay. Hookean solid has dash compliance and the relaxation model, that is part 1 of the question. So what kind of compliance does Hookean solid have? So compliance, it comes in creep experiment. So creep experiment is you apply a constant stress and identify the change in strain as a function of time. So compliance is change in strain as a function of time divided by the constant stress that is being applied. So how does compliance look for a Hookean solid? Okay, you're saying creep. Hookean solid has dash kind of compliance. How does the response look like? How does the compliance look like? And the next part of the question is the relaxation modulus for viscous or Newtonian fluid is, again, how does it look like? How does it look like? It is actually For Hookean solid, you know, it is a constant compliance. Okay, because once a particular stress is applied, there is a particular strain that is reached, and the value of compliance is constant. It is an instantaneous value. That's it. Whereas in and then the part 2 of the question is relaxation modulus for a viscous solid or Newtonian fluid is 0, because the material completely relaxes and it's completely fluid like behavior. That means the modulus, the solid like behavior is 0. Okay, so that is what is the answer for this. So this is how it look, you arrive at this. So there is an instantaneous strain for the stress applied. So your compliance is, the compliance as a function of time is nothing but equal to the compliance at initial value, and then it is maintained. This is the compliance that is maintained. Okay, and similarly, your relaxation modulus, it comes in the concept of stress relaxation, where a constant strain is applied and your stress is identified as a function of time. So stress is a function of time over constant strain is the relaxation modulus, and there is an instantaneous decay in case of a viscous material or a Newtonian fluid, completely viscous or perfect viscous material or a Newtonian fluid. So that is why your uh, the relaxation modulus is 0. E of t is equal to 0. Okay, next question. According to Maxwell model, for oscillatory response, as the frequency increases, dash response dominates, while the dash response dominates at lower frequency. So, which kind of response dominates at as the frequency increase or at higher frequencies, and which kind of response dominates at lower frequencies? Yeah, I think you said this for a previous question, the no recovery, right? The relaxation modulus. Okay, this question you have no idea, don't, no worries. So the answer is, as the frequency increase, you can find the elastic response dominating, while the viscous response dominates at low frequencies. Okay, because at low frequencies there's enough time for the material to relax. So the material starts relaxing, more and more. There is much more of the relaxation process that is happening. So the viscous behavior dominates. Okay. So here you could see, the G double prime or the E double prime is higher than that of the uh, storage modulus. Okay. Whereas as you increase the frequencies, your storage modulus, material has literally no time to relax. So it shows more of a solid like response or elastic response. Okay, more of a elastic response. Okay, now the you're able to follow. Okay, good. Next question. 1 by 2 into eta into strain square is energy dash during a stress strain cycle. Is it you know energy storage or energy dissipation? This expression is a expression for energy storage or energy dissipation. Which of these corresponds to? This was discussed while there was a discussion on damping. So any thoughts? Okay, no worries. It is actually the dissipation. So when you calculate the work of dissipation, you will get into this expression of half into eta into uh, strain rate the square. So if you actually separate the terms, it is eta into e your strain rate into strain rate. So eta into strain rate is nothing but your stress. So stress into strain rate. Okay, now that will give you uh, your energy per unit volume of or rate of work. Okay, so this actually gives the dissipation during a stress strain cycle. Next, damping behavior increases with strong secondary interaction. Identify if the statement is true or false. When there are more secondary interactions, the damping behavior increases. Is it true? Okay, I'll just proceed. It is actually false. So the damping behavior actually decreases with strong secondary interactions and crystallinity. Okay, when secondary interactions are high and the crystallinity is there in the material, then the material damping behavior decreases because damping behavior mainly depends on your dissipative mechanism of energy. And under these secondary interactions, if there are strong secondary interactions, then there is more storage. Okay, and similarly in case of a crystallinity, so the dissipation is lesser. So the material, the damping material should have more of dissipation. It should be able to dissipate energy, then only you will not have that vibration transferring, right? It should dissipate the vibrations. For example, when the rubber is placed between two vibrating materials, it has to dissipate energy so that the vibration is not transferred. So when there are strong secondary interactions or crystallinity, this damping effect will be lesser because the material is unable to dissipate energy. Okay, shall we proceed with the next question? Okay. Temperature affects all relaxation modes identically. Is it true or false? So, for different relaxation mode, the effect of temperature, is it same or is it different? Okay, you're saying false. Why do you say it is false? Different elastic viscous have response. Okay, to temperature. It is not about the elastic and viscous response, but like different relaxation modes, like whether the relaxation mode due to secondary interactions or due to the macromolecular, there will be segmental relaxation, subsegmental relaxations, right? So whether the effect of temperature is same in all relaxation modes, it is actually true. The effect of temperature is same in all relaxation modes, and this is what is one of the basic principles. It is almost same for all relaxation modes, and this is what is one of the principles used for your time temperature superposition. Okay, you're able to get it. So for example, at lower temperatures, the relaxation modes, whether it is going to be segmental or segmental, when the temperature gets decreasing, so the relaxation process is not going to happen. Whereas as the temperature increases, the relaxation process, happens, whether it is going to be subsegmental or the whole segment or the whole macromolecule, it is going to happen, it's going to increase, right? So the overall effect is going to be the same. So that is one of the, basic aspects. The temperature affects all relaxation modes identically. Next. ISO test is based on per unit of dash of crack. So we have two different types of tests. One is ISO test and Charpy test. For understanding the impact behavior. So what is the unit of this ISO test? Any thoughts, or let's proceed? Probably. So it is actually per unit length. So in ISO test, it is joule per unit length of the material. That is how your impact energy is uh, done. Whereas in case of Charpy test, it is per unit area. Okay. Actually, that's it with the session. I mean, that's it with the question. So, do you have any other doubts? Any other doubts on whatever we have discussed so far in this session? Or any other doubts overall do you have? Uh, no. Okay. So, you don't have any questions. So, you were able to follow the session, right? Yeah, sure. Definitely post. If you have any doubts, please post it in the forum, or else you can ask in the live interactive session also. Okay, make use of the forum as well as the live interactive session for asking any doubts, and also, be more interactive, and so that it will be a learning process for all. Okay. Okay. So if no more questions, then we can officially end the session. Thank you. So you can also, say if we could add something to the live interactive session so that, it will be more useful for all of us. So you want more questions, more concept related questions or more problem based questions. So, you know, those kind of things, or some other, additional information that can be added to the session so that it will be useful for everyone. You can also give a feedback on the live session. Okay. And if you're not able to follow, the explanation given, no, so please let us know so that we can, improve the session. Okay. So that it will be useful for everyone. Okay, scribble pad for 5 minutes, not just topics to be placed as like contents. Okay. Okay. Sure, sure, sure. So, so you need some, okay, a bit of explanation, much more, explanation. Okay. So, yeah, sure, sure, sure. We'll, increase the, recap of the lecture content, you know, you know, to a little more explanatory, explaining. Okay, sure, sure. Because the expectation is that most of you would go through the lecture content and come, so that it will be just the glimpse of the, session. Sorry, glimpse of the lecture content, but I could see many of you are not able to actually, go through the lecture contents before the live interactive session. So I'll try to increase the explanation to much more, level. Okay, so that it is useful and you're able to interact during the, when we are doing the practice assignment session. So definitely we'll do that. Okay, sure. Thank you. Thank you. So let's officially end the session. Thank you all.